All right, I'm going to complete the lecture here with forces on current carrying wires. We talked about this scenario in class. I'm going to go through it one more time just to have it make sense, hopefully. Let's look at the magnetic fields that these two wires are going to generate. So the one on the left, the blue wire, is going to generate a magnetic field, and you can figure it out with your curly hand rule. So on the right side over here, it's going to have a magnetic field that's going to be going into the paper, okay, or into the page or the screen or whatever. So on this side, you're going to get a magnetic field that goes into the paper. And then on the other side, you're going to get one that comes out. So coming out at you, I'll put little dots. Now, that's the magnetic field due to the blue wire only. Now, what about the magnetic field due to the green wire? Well, on the right side, it's going to be having a magnetic field that goes into the page. And then on the left side, it's going to have a magnetic field that comes out of the page. Now, it's important to understand that moving charges along a wire, so I'm going to make it red so you can see it. So if I'm a moving charge and I'm moving along this wire and I'm going up there, I'm only going to feel a force due to the magnetic field of the other wire. I can't feel a force due to the magnetic field of my own wire. So what magnetic field is going on over here due to the green wire? Well, since I have a force magnetic field coming out at me, I use my right hand rule, thumb in the direction of the charge moving up, magnetic field towards me is going to feel a force towards the middle. Let's look at a charge over on this guy. So here's a charge over here, it's moving up this way. What's happening in the magnetic field? Well, the magnetic field over here on the green wire, I have to look at the blue X's. I'm only going to be concerned about the magnetic field created by the other wire, not by the magnetic field created by my own wire. So I looked at the blue X's. Okay, my thumb in the direction of motion, my fingers pointing into the page, it's going to feel a force to the left. So what we find is when we have two current carrying wires that are moving in the same direction, they're going to feel a force that pulls them together. Okay, and there's the forces pulling them together. Now, if we have currents going in opposite directions, we can do the same argument. Okay, let's figure out, I'll do green magnetic field lines first. I'm going to have X's over here on the right, and I'm going to have dots over here on the left. And they're not going to be uniform, but I'm just going to show them to show what's going on. Okay, then blue. What's the magnetic field going through the blue wire? Okay, so because it's now going down, I'm going to have X's on the left due to the blue wire, and I'm going to have dots on the right. Okay, so let's think about forces now. If I have a charge over here on this wire and it's moving down, okay, and due to the green magnetic field, the magnetic field is going to be going out of the page. So moving out of the page, with my right hand rule, I'm going to figure out that the force is going to be going that way. Okay, so test that for yourself. And then finally, if I put a charge over here and I move it up, and I'm in the magnetic field, the blue magnetic field lines, that's what I'm paying attention to because I'm only going to be affected by the magnetic field due to the other wire. I put my thumb in the direction of motion, and then I think about the direction of the magnetic field with my fingertips, and the force is going to be out. So when you have two current carrying wires moving in opposite directions, there's going to be a force that pulls them apart. Yes, nice metaphor for life. Okay. And there's the answer already shown, so that's not so helpful, but let's look at this anyway. Magnetic field midway between two straight wires carrying equal currents in the same direction is parallel to the wires, perpendicular to the plane of the wires, 0. It's going to be B, perpendicular. So if you have two, let's do this. Okay, so if you have two wires, okay, carrying direction, so you have a wire here and you have a wire here, and they're both going to be having currents going in the same direction. You think about, I'm going to make this one green, okay? So this one's going to be green. If it's going up this way, magnetic field in the center, well, due to this current carrying wire, the magnetic field is going to be coming out at us, right, because of the curly hand rule. And then due to this wire, the red one, the magnetic field is going to be going into the page. Oop, that's supposed to be red. Into the page. And so in the center, they're going to exactly cancel each other out. And because they cancel out, the answer is C, 0. So I don't know why there's a B there, but yes. When you have two parallel wires, currents going the same direction, they're going to cancel each other out in the exact middle, so the magnetic field will be 0. Force between two parallel wires carrying currents in the same direction is, we just demonstrated that. If they're going in the same direction, then they're going to feel a force that pulls them together, or be attractive. All right, example problem. Find the magnitude and direction of magnetic force on a 1.5 meter long straight wire carrying a 5.0 current upward in the magnetic field of 0.40 Tesla pointing out of the page. Okay, so this is just an F equals BIL problem. So the force, find the magnitude and direction of the force. Okay, so we have a 1.5 meter long, so the force is going to be, well, the magnetic field is going to be 0.40 Tesla, and it's pointing out of the page, so the magnetic field is going to be going like this. Okay, so here's a magnetic field coming out of the page. A long straight wire carrying a current of 0.5 amps. Okay, so that's going to be 0.5 amps. And the length is 1.5 meter. And the current is going upward, so the current is going to be going upward, okay, in a magnetic field that's pointing out of the page. So that means the force, get out your right-hand rule, okay, you have your magnetic field coming out of the page, and then you have your charge moving upward, so the force is going to be to the right. So there's your force. Okay, so the force is going to be, well, I don't know what that's going to be. I'm going to have to multiply it out. Let me pause and multiply it out for you. Okay, so I got 0.3 newtons, and it's going to be to the right. Okay, next problem. Okay, one thing to think about is the effect of moving charges in a magnetic field you can use to measure the currents. So a simple meter is going to detect a current in a small magnetic needle on a pivot. So basically we call this a galvanometer. So your ammeter or your voltmeter, these are all examples of meters that are going to change their behavior based on the amount of current going through a loop. So when electric current passes through a coil, each loop is going to affect the needle, and so we can use that to measure current. So if you get a big strong current, it's going to really make the needle move. If you get a weak current, it's only going to move a little bit. That's what your ammeter is doing when we had those analog ammeters working on your labs. So if you want to think about what's happening, I'm going to pause. You should pause the video. I'm going to pause it too. But take a look at the video. I want you to think about the coils and how they're rotating around. Think about the direction of the magnetic field. And think about how, when you have coils of wire with moving currents, you're going to get that thing to rotate. Okay, so pause your video, look at what's going on, and think about how a current is going to cause this thing to move. Okay, so imagine, let's look at this side over here. Imagine on these little coils, you have on these blue dots represent where current is coming towards you. So put your thumb in the direction towards you, little dots of current coming towards you along that coil because it's wrapped around and around. As the current comes towards you, put your fingers in the direction of the magnetic field, for the north to south. Then you're going to feel a force that tends to push it this way or cause a torque. And that torque is going to cause the needle to rotate, and that is going to be an indicator of how strong the current is. It's going to rotate more if you have a stronger current because it's going to feel more of a force. So again, this is hard to conceptualize, but you got to sit and think about what's going on here. A loudspeaker, and here's a little link. You can get this off the PowerPoint online. You can check to see exactly what's happening with a speaker and the north-south magnetic field. But you bring in a current. The current is going to set up, once you get a current going through your coil in a magnetic field, it causes a force and it causes this thing to move back and forth. And it's that vibration at many, many hertz. Remember, it was like I think around 1,000 hertz you can hear pretty well. About 20 hertz is like the limit of what you can hear. But as you get higher than 20, then you can start to hear, and as the speaker vibrates, you can develop sound. So that's what a speaker does. It has a magnet, it has a current. The current goes through, and the current will vary. As the current goes through the wire, it feels a force, and it pulls the speaker in one direction, and then it pushes it back the other way by changing the direction of the current, etc. Mass spectrometer is kind of a cool device. So imagine what we have here is you have a magnetic field. These little dots represent magnetic fields coming out of the page at you, and you're going to send in little particles. So you'll send little particles in here into a magnetic field. You're going to give them a little kick. Okay, you can give them a little kick and send them into this magnetic field. And depending on how massive they are, like if they all have the same amount of charge, a more massive one is going to go. It's going to have a larger radius, and it's going to follow this track over here. And then a smaller one is going to follow this radius over here, because the force, if the charges are the same, the force is the same, but then because the acceleration is going to be more if it's less mass, you're going to get a tighter circle for a smaller mass. So this is a mass spectrometer. It's a way of taking isotopes that have the same element, have the same chemical properties, so they might have the same amount of charge. Can't tell what they are, so you throw them in a mass spectrometer, and they're going to curve more, and therefore you can identify which ones are which based on how much they curve in a magnetic field. Finally, a DC motor. We're going to spend a lot of time talking about a DC motor and how they tend to work, but this is a really powerful application. So in a DC motor, you're going to have current going into a wire. Okay, so here's your battery. So you have your current coming in here into your wire. And then as the current goes through, let's take out this bottom part of the coil. As the current goes through here in this direction, okay, and you have a north-south magnetic field, so the field is going, let's do a different color. The field is going this way, okay. You have a field going this way and a current going this way. Again, you're going to get a torque, and the torque is going to cause a force to act in, let's do a different color, in this direction. So the bottom part of a little coil is going to feel a force this way, and then the top part is going to feel a force that way, and it's going to cause a torque to happen. So if I draw it this way, you kind of then you're going to get a force this way down here and a force that way down there, and it's going to cause the thing to spin. And that's what's happening in a DC motor. Is you put a current through a wire, you do it in a magnetic field, and it's going to cause a torque that causes something to spin. Now, normally it's going to spin, and it's going to get to this position and then stop, and it won't feel a torque anymore because now the direction of motion is parallel to the magnetic field. But we get what we call a commutator, and again, this is just a brief introduction. That will cause it to switch directions, and that way you can get it to keep spinning. Here is a cool animation. If you go check it out online, you get a sense of what's going on with DC motors. We're going to spend a lot of time talking about DC motors and then how having them work in a magnetic field can cause them to move. And that's basically what a motor is. It's just a coil in a magnetic field. It feels a current causes a force, it causes the thing to spin. All right. Well, that concludes our lecture. Thanks for bearing with me today. Sorry it was so long. And we'll see you tomorrow for the lab.